3.4 is polynomial functions, graphs, and models. We are going to look at polynomial function in behavior, behavior around zeros, and then try and graph and also figure out what equations are, what these functions are based on a graph. So we've got a lot to cover. I have several examples here. I want to start by connecting this information to something that you already know. Let's see if we can think of an example of a positive first degree function. Looking at something that's positive in first degree looks something like this, okay? And a positive second degree, maybe something like y equals x squared, that's going to look like this. Now I'm only looking at the ends, so I'm going to put this little censor box right here, censoring our math. Don't really care about what's going on there, but we are wanting to focus on what's going on at the ends. And a third degree positive, if you remember, y equals x cubed looks something like this, right? And again, I'm going to censor what's going on there because we could have some different things going on, as you'll see during this section, but we just want to focus on what the ends are doing. And doing the same here. Fourth degree positive, could be doing some stuff there in the middle that we don't know yet what it is because we don't have an actual function, but I do know that the ends are going to do something like this. And a fifth degree, you may have guessed, is going to look similar to the third degree. And you know, if we did the same thing here, we don't ever look at what's in the middle of that graph. The end behavior, you can see a pattern. If it's odd, then it's starting down here and ending up here. Starting down here, ending up here. Starting down here and ending up here. So that is odd and positive, okay? Odd degree, first degree, third degree, fifth degree, seventh degree, 19th degree, etc. The ends of the graph are going to be doing that if it's odd and positive. So one way that you can think about the being positive, first this would be like a y equals positive x, y equals positive x squared, and so on. But if you would take the average rate of change between here and here, you can say that it's positive, okay? Here to here, that's positive. Here to here, that's a positive average rate of change. As far as the evens go, you're thinking about the happy parabola, right? You've got the happy parabola, there he is, and this one is also a happy parabola. So evens will be going up and up like that if they are positive. Okay, let's talk about negative first degree. So y equals negative x would be an example of something like that. Let's cover up the middle. We don't care about what's going on there. We care about what is happening at the ends. And it's going to go down like this. And you guessed it, the parabola would be going like this. My cubic, if it is odd and negative, it's going to be doing something like this. And here, fourth degree and negative, the ends are doing this. Fifth degree and negative, again, doing something like that. So we have odd positive, we have even positive. Up there, we have odd negative. Odd negatives would be like this, and this, and this. And again, think about what the average rate of change is from here to here Well, I do know that it's negative. It's going down. From here to here, it's negative. Here to here, it's negative. That is even and negative. Then here we go. We've got a sad face here, sad face here. So there are two things that determine your end behavior. It's the degree, if it's odd or even, and if it's positive or negative. And a polynomial is positive if the leading coefficient is positive. It's negative if the leading coefficient is negative. So there's some of the notes that you took in your at-home notes talking about the end behavior. This is the way they would write it in calculus. If we have an odd degree and a is positive, a is your leading coefficient, then as x approaches positive infinity, then y is approaching positive infinity. Okay, so as x goes to the right, y goes up, and as x approaches negative infinity, f of x approaches negative infinity. So as x goes to the left, y is going down. Okay, so it's that type of language all the way through here. For us to be able to categorize these a little quicker, we can just use these little end behavior symbols of a down, up, an up, down, an up, up, and a down, down. So here we're going to use that end behavior diagram that we just circled on the at-home notes to describe the end behavior of this graph. Remember, it's all dependent on that leading coefficient and the degree of the polynomial. So we have a negative as our lead coefficient, -1, and the power, the degree of that polynomial is odd. So we're odd and negative. So it's either going to be up like this or like this. If it's odd and negative, remember your overall average rate of change must be negative. So it has to be this type of behavior. So let's write our symbol up as you go to the left and down as you go to the right. Here's our lead term. We are positive and odd. Positive and odd, that means we're going to be positive. Our average rate of change from beginning to end is some number that is going to be positive. This is positive and even, so he's like that happy parabola, okay? Something like this. Keep those middles open. You don't want to write those. We don't know what's going on in the middle with those. We'll work more on that later. And here, this is not our leading term. This polynomial is out of order. The highest degree term is your leading term, no matter where it's placed in that polynomial. So we have a negative and an even power, a negative coefficient, even power, and that's going to give us the frowny face parabola type of shape. Okay, this is not a parabola, but it has the same type of end behavior as a negative coefficient parabola. All right. Behavior of a graph near zeros. I've written different multiplicities here. So I want to do a very easy example here. Y equals x is an easy graph here, and your y-intercept is 0, 0. Okay. What does y equals x squared look like? Well, again, 0, 0 is your 0. But what does the graph do as it gets to 0, 0? What it does, here's your 0, 0. What it does is it comes down to it and it touches it and bounces off. Okay? multiplicity of 3. So we're talking about something like y equals x cubed, going something like this. Okay. And again, that's 0, 0 is your y-intercept. So your 0 is 0, and it's going through it. Fourth degree polynomial. Something like this. Okay. Again, y-intercept or x-intercept is 0, 0. Your 0 is 0. It comes down and touches that 0 and then bounces back up. If you have a fifth degree, you guessed it, hopefully, it's doing something like this. Okay. So you can see a pattern. Again, if it's odd, it has an odd multiplicity, then it's going to go through that 0. Now the higher the power, the more flattened out it gets. I didn't really draw a very good graph of this one. More flattened out that it gets as it goes through that 0. So your y equals x to the 5th graph, it's going to look a little more flattened out as you get close to that 0. The behavior of the graph near the zeros. Okay. And if we have an even power, then it's touching and bouncing off. The odds go through, the evens touch and bounce off. Even if it were a negative, okay, so if we had something like this, y equals negative x, y equals negative x squared, touches it and bounces off. Okay. Y equals negative x cubed. Again, it goes through. Y equals negative x to the 4th, and it flattens out a little bit more than a y squared does. You can compare those graphs on a graphing calculator or in Desmos and see that. Y equals a negative x to the 5th. Again, negative in behavior, and it's going to flatten out a little bit more than the negative x cubed did, but it definitely has a curve as it goes through 0, 0. Don't have a bouncing type of behavior there. All right, graphing a polynomial function. If you have some polynomial function of degree n, you want to follow these steps. First, you find the zeros of f, the real zeros, and plot those corresponding x-intercepts. We're going to find that with factoring, with synthetic division, with long division at times. Find f of 0. That is going to be your y-intercept. And that's an important part of your graph. Don't make it all about the x-intercepts. And then use your in behavior and whether the graph crosses, bounces on, or wiggles through x-axis at the x-intercepts, and selected points as necessary to complete the graph. It is important that you know this isn't really graphing the polynomial function. We are really just sketching. It's going to be a rough sketch. There are some other finer details of these graphs that we're not going to worry about. You will know how to do those once you get into calculus and learn some more of the math that you need in there. But don't worry about right now. I'll show you what's important. Relationships among x-intercepts, zeros, solutions, and factors. So this is all vocabulary that you will need to know and use correctly. So if we have something that you have an x-intercept of the graph that is c0, you know that's an x-intercept because the y is 0. Then that means that c is a 0 of f, because you know f of c equals 0, giving you the point c0. C is also a solution of f of x equals 0. So if you were to set that function equal to 0 and solve it, c is a solution. And if C is an x-intercept, sorry, C0 is an x-intercept, that means C is a 0 of f, which means x minus C is a factor of f of x. All right, let's see if we can sketch some of these polynomial functions. I have a few examples. We'll start with this one. This is already factored for us, so if we would set each factor equal to 0 and solve, then we would have the x values, your zeros of the polynomials, and so we have a 4x is -3, x is -3/4, and here take the square root of both sides, we get x plus 2 is 0, and x is -2. So my zeros are -3/4 and -2. Go ahead and write this out. The zeros are -3/4 and -2, which means my x-intercepts are -3/4, 0, and -2, 0. So we can go ahead and graph those. Here's my -2, 0, and my -3/4, 0. And don't forget the y-intercept. Remember, how is it that you find a y-intercept? Find a y-intercept by making x 0. So we're going to find f of 0. So f of 0, 4 times 0 plus 3 times 0 plus 2 quantity squared, which is 3 times 4, which is 12. So that means that when x is 0, y is 12. Don't feel like you need to put all of these dash marks up there. Just make one dash and call it 12, because you're not going to have anything else on that y-axis where you need to establish some kind of scale. Okay, now remember, your end behavior is fully dependent on your leading coefficient. So think about what would happen if you actually multiplied this out. We would have first the squaring of x, so that would give you x squared plus some other things, and then that would get multiplied by the 4x, so you would end up with 4x cubed as your first term, then plus minus a bunch of other things. So we have a positive 4 and an odd. If it's odd and positive, that means we're going to start down here and end up here. Okay. Now behavior around your zeros. If you notice, this one has a 2 exponent on it, which means this has an even multiplicity. You're going to bounce once you get to that -2 on the x-axis. So one thing I like to do, so I remember to do this as I'm drawing, is just put a little dashed halo around the graph, and that reminds me to go ahead and bounce when I do my graph. Okay, so I'm going to start down here, and here we get this little dashed circle there. Makes me remember to bounce. And this one is going straight through. And then we also have this that we're picking up as we go through. And that's it. Now you can pay attention to if you have a linear factor like this, that is a 0 of just multiplicity 1. If you zoom in on this, -3/4 right there, it looks, if you ignored the rest of the graph and you only looked at this part, it almost looks like a straight line going through there. You don't have any kind of a curviness going through like you would with a higher power of odd function. So that's something to note. And if you look at the 0 that has an even multiplicity, erase that other arrow, and 0 the other zero that has an even multiplicity of 2, it bounces off of it. And again, if you would zoom in on it and only look at this piece of it, it looks almost like a parabola, okay, with the even multiplicity going on. It's kind of a neat way to think about how all these graphs come to be. All right. We want to try another example here. Let me get this behaving correctly. All right, try this one. Now this one I already know is even and positive. My leading term is 3x to the fourth, so it is positive and even. It means I'm going to have an up type of behavior when I graph this. But our job right now, so that we can figure out how this is going to graph out, is we need to get our polynomial factored. So don't jump automatically to synthetic division. Synthetic division is a tool that we can use if something doesn't factor by our usual methods. But I have a greatest common factor of x squared, which leaves me with 3x squared plus 5x minus 2. And I'm going to go ahead and finish factoring here. And so now I can see my zeros are 0 from this factor with a multiplicity of 2. That means when I get to that 0, it's going to touch it and bounce off. I have a 0 from this factor of 1/3, multiplicity of 1. So when it goes through it, it's going to go through like a linear function at that 0. And a 0 of -2 with multiplicity of 1. And then my y-intercept, these are your zeros. You can make those x-intercepts out of that. My y-intercept, though, is 0, 0. If I make all of my x's up here 0, then y is 0. So should make sense that if we have an x-intercept of 0, 0, it's also a y-intercept. Okay, so these are the x-intercepts that you get from the zeros that we found. Let's go ahead and graph those. I have 0, 0. I have a 1/3 0, and I have a -2 0. Remember that that 0 has a multiplicity of 2, so you can go ahead and put your little halo around it to remind yourself to bounce once you get there. And we have everything that we need to go ahead and draw this. So we're going to start up here, like we said with our end behavior. I'm going to start up here and go through this like a line, bounce off like a parabola, and go through like a line. And that's it. We have a nice sketch. Now don't worry about how deep you're supposed to go on these or how steep those arrows are. Remember, this is just a sketch. The important thing is that you have the correct x-intercepts, you have the correct y-intercept, you have the correct behavior around the zeros, you have the correct end behavior, and that you're above the x-axis when you're supposed to be, and you're below the x-axis when you're supposed to be. So if you go to graph this and it looks really different from what you have, you might check, make sure those key things are the same. As long as those key things are the same, you've got a pretty decent sketch going on. All right, let's try this. And this one has quite a lot of factoring for us to have to do. So we are going to start with our possible rational zeros. Our possible rational zeros are going to be plus or minus 1, 2, 3, and 6. I'm going to set up my synthetic division and start. with dividing this. 1, 3, -3, -11, -6. I always like to start with 1. 1 times 1, you get 4, 4, 1, 1, -10, -10, -16. Oop, not -116. And that did not work for us. It's not useless information though. You do know that you have the point 1, -16 on the graph. So if you wanted to keep that on your synthetic division work and use that as a point to graph, you could do that. It's not required, but I have this 2, 5, 10, 7, 14, 3, 6, 0. And so 2 is one of my zeros. Now it could be that it works again, but actually not. If you look at this, we would make a new list of possible rational zeros, and the new list of possible rational zeros here is just plus or minus 1 and 3. I already know 1 did not work. If it didn't work in the bigger polynomial, it's not going to work for part of that polynomial. So we'll throw out the 1. We could try a 3. Let's go ahead and try a 3. So I'm going to put a new synthetic division table with my reduced polynomial, the quotient from that last one after I took out the 2, and I'm going to try putting 3 through it. So 1, 3, 8, 24, 31, 93, 96, and definitely did not work. So we're finished with trying 1 and 3. We can try a -1. So I'm going to rewrite this here. 1, 5, 7, 3. I'm going to try a -1. 1, -1, 4, -4, 3, -3, 0. So we found yet another 0 of -1. So zeros of 2 and -1. I'm left with a quadratic of x squared plus 4x plus 3. And I can factor that as x plus 3, x plus 1, which means that -1, let me go ahead and write this out vertically, -1 is a 0 of multiplicity 2. And -3 is also a 0. So there are my 4 zeros. Again, we have a positive 1 x to the 4th, so it's a positive and even. It's going to be an up and up. I have zeros of 2, -1, -3. And my y-intercept, if I would put 0 in all of my x's, I get a y of -6. So again, just one tick mark, label it with a -6. Remember that your 0 of -1 has an even multiplicity, so it's going to bounce off of it, kind of like the behavior of a parabola. And the other are linear, so we're going to go through those like a line. Okay. So we're going to go through this one like it's a line. We're going to go here and bounce off of that and hit our y-intercept down here. I don't know how far down we go. It doesn't really matter with our sketch. We're going through here and we end up somewhere over there. So this is roughly what our graph looks like. It's got all the important stuff that we want for you to be able to handle in this class. Right, the intermediate value theorem is something you wrote down with your at-home notes. And this is a polynomial function with just real coefficients. If for real numbers a and b, the values f of a and f of b are opposite in sign, then there exists at least one real 0 between a and b. Let me demonstrate what this means. It means, okay, we have some kind of a polynomial going on here. Let's say that you put a number like -7 into your synthetic division table, and out pops a 4. Okay, out pops a 4. And if you put in a number of -2, out pops a -2. So that means that over here at -7 we were above the x-axis, and over here at -2 we were below the x-axis. So we know that there exists a real zero somewhere between -7 and -2. That is the intermediate value theorem in a nutshell. All right, it's kind of what I call the chicken crossed the road. We know he was here at one point in time, and then at another point in time he was on the other side of the road. So you know somewhere between -7 and -2 he did cross the road. All right, they want us just to demonstrate by the intermediate value theorem that we have a zero between 0 and 1 for this polynomial. So we're setting up our synthetic division table. Remember to watch for your negative signs and any missing terms. I'm going to put 0 through it. Okay, so 0. There we go. And so I know that I have this point 0, 7. And then let's try putting in a 1. If I put in a 1, it's 2, 2, -3, -3, -8, -8, -1. And so I have the point 0, 7 and the point 1, -1. Therefore, change of sign here shows there is a real zero between 0 and 1. Okay, you can do the same thing with this next problem. Let's go ahead and write out, oops. Let's go ahead and write out our synthetic division table. So 1, -4, 0, -1, 3. Don't forget that there's a missing x squared there. And we're going to put in a half. So here we go. 1 times a half is a half. That is a -3.5. Let's go ahead and keep that as improper. That's a -7/2. -7/2 times 1/2, that's -7/4. -7/4 times 1/2, that's a -7/8, and that's a -15/8, and multiply by it, that's a -15/16, and add 3. I do know that some positive number, you don't even have to tell me what the number is, okay? Well, let's try putting a 1 through there. Same synthetic division table. 1, -3, -3, -3, -3, -4, -4, -1. And again, you don't even have to tell me what the number is by the end. I know because there was a change of sign right there. A change in sign between 1/2 and 1 shows there is a real zero between. Okay. All right, now we're to some of the graphing problems. These are functions that have already been graphed, and we have to figure out what the function is that comes up with the graph. All right, so we could start out by finding the zeros. Let's see, this is -1, -2, -3 is a 0, and it goes through it straight. So we're going to do x minus a -3 is one of the factors. And then I have a 2. Sorry, that's a 1 with the scale. This is a 1 right here. So that's going to be x minus 1. And this is 2. So x minus 2 is another factor. And it looks like they're just kind of going straight through it. It doesn't look like there's any higher degree than 1. If those were cubic, we know first off they're odd because it goes through. But if they were cubic, they would kind of flatten out as they went through the 0. Neither one of them are doing any of that. Okay, they're just kind of smoothly going through. Okay, so I know that I have f of x equals some kind of number in front. We're not guaranteed that it's just a 1. Let's go ahead and work this out. This is a times x plus 3 times x squared minus 3x plus 2. F of x is a times x cubed minus 3x squared plus 2x plus 3x squared minus 9x plus 6. So f of x is equal to all of this times the a. Now, what I do know now is I also have this point of 0, 3. That means that when all of my x's are 0, then my f of x is 3. So I can replace this f of x with a 3. I've got my a. And if this is 0, 0, 0, 0, 0, those go away, I get just a 6. Okay? So a is 1/2. Now you're going to have to go back and backfill that function that you made. So this is a f of x equals 1/2 times my x cubed minus 3x squared plus 2x plus 3x squared minus 9x plus 6. That's all in expanded form. And so f of x equals 1/2 x cubed. I can put my x squareds together, they go away. I can put my x's together, I get a -7/2 after multiplying by the 1/2 x plus a 3. And most definitely when you look at it in its finished form, it's a lot easier to see that you have a y-intercept there of 0, 3. And it doesn't have to be the y-intercept that you use that way. I could have used this point up here, which is a 3, 6. I could have used a 3, 6 in there. So make all of the x's 3, make the f of x a 6, and then solve for your a. But that's how you do that. And you should be good to go for your 3.4 homework. Just let me know if you have any questions.